Hi everyone, I'm Eric Tao. This is one of a series of videos from the Reimagining Pre-Calculus project. Our goals here are to give you a brief accessible introduction to a key course concept from pre-calculus and then tie those to real-world applications. In this video we'll be doing something a bit different. We'll look at what I call the hierarchy of functions. And our objectives really come in two different forms. So our first two objectives are to look at the hierarchy of numbers. So there's four kinds of numbers that we'll consider: integers, rational numbers, algebraic numbers, and transcendental numbers. In our second objective for this video, we'll compare that to a similar list of functions. So we'll look at polynomials, rational functions, algebraic functions, and transcendental functions. And then after that, we move on to our next main goal, which is to consider how to evaluate all of these different function types. So we'll look first at evaluating polynomial, rational, and algebraic expressions in functions. And then last, we'll look at how to evaluate exponential and logarithmic functions. Let's start by considering some different kinds of real numbers. And the way I'll do it here is divide the real numbers into four different kinds. Let's start at the top. We'll look at integers. These are whole numbers, numbers like 2 or 0 or -1. We have positive and negative and 0. And one thing about real numbers that are integers is that if you add or subtract or multiply integers, you will get new integers. So that's something about integers that we rely on, we tend to take for granted. We can move on to another set of numbers, another type of real number, which would be rational numbers, or sometimes called fractions. For fractions, we're looking at ratios of integers. So that might include -1/2, or 3/2, or even numbers like 2/1. And of course, that's just the number 2, which tells us that integers are all technically also rational numbers. And for those types of numbers, we can do four different arithmetic operations. We can add, or subtract, or multiply, or divide. If we do any of those four operations, as long as we don't divide by 0, we get new rational numbers. The third number set, and this is one that you might be less familiar with, we call the algebraic numbers. And so these are numbers where there may be roots involved, square roots, cube roots, any kind of root at all. And that might give you numbers like the square root of 2, or even more complicated things like this fraction that I have, 1 plus the cube root of 3 in the numerator, and then the square root of 1 plus the square root of 2 in the denominator. So you can have roots inside of roots here. And the thing that distinguishes the algebraic numbers from the others is that in addition to having four arithmetic operations that you can also take roots. So what I mean by that is we can add or subtract or multiply or divide or take roots of algebraic numbers, and we'll get new algebraic numbers out of it. So those three taken together give us most of the numbers that we could conceivably run into in a math class. We like working with integers the most, but progressively we can expand our horizon to include stranger numbers, so fractions, roots, what have you. There's one other set of numbers that are a bit harder to get your head around. We call these transcendental. They transcend the algebraic nature of the other numbers. And all that means here is it's a catch-all term for numbers that aren't algebraic. So everything, integers, rationals, algebraic numbers, they're all sitting in this universe of numbers, and everything else gets called transcendental. So that includes numbers that are more strange, numbers like pi or e, and there's lots of others. Pi and e are the ones you'll see the most often. So this gives us a way of categorizing numbers. We have our set of real numbers. We can look at the different types within that. And it gives us a way to organize it in our minds so we can use these ideas as we work with numbers later on. By comparison, we can do the same thing with functions. So as we've worked with functions, we can make similar observations. And it turns out there's a nice analogy between the real numbers, those 4 kinds, and then the 4 kinds of functions. So let's go through the 4 kinds of functions, and we'll see how similar these categories are. So when we look at functions, the simplest kind in our list are polynomials. So these are positive powers of x, possibly with a coefficient in front. I've given a couple examples here. We have x squared plus 1. That's a fairly simple polynomial. It's a quadratic. A quadratic polynomial is one where the highest power of x is just 2. But it could include lots of other types of polynomials. It could be things like x cubed minus 5x plus 1. And really any positive power of x, including a possible constant term at the end, gives us a polynomial. Turns out one nice thing about polynomials is you have the same 3 arithmetic operations in play that you had with integers. So for polynomials, you can add 2 of them together, you can subtract 2 of them, you can multiply, and if you do any of those 3 operations, you will get a new polynomial back. So in a lot of ways, you can think of polynomials as the function version of an integer. It's just like a whole number function. We can move down the list to rational functions next. Those even have the same name. Rational means ratio. It's a fraction. Just like we had rational numbers, we can have rational functions. And you can get things that have polynomials on the top and the bottom. So you may have something like x over x squared plus 1. You may have something a bit bigger, like x cubed minus 2x over x squared minus x minus 1. And those polynomials can be as big and as complicated as you want, but the point is that they're in the numerator and denominator of a fraction. And just like with rational numbers, we have another operation we can do. It's division. And as long as we don't divide by 0, we're able to add or subtract or multiply or divide any rational functions to get new rational functions. The third category is the same name as before with numbers. They're algebraic functions. And you can see the analogy here. If I take roots, possibly with fractions involved, possibly with polynomials involved, I just throw in roots of any kind, I get things like the square root of x. I might get something more complicated. I could have a fraction with roots in it, so the cube root of x over 1 plus the square root of x. And what we've done now is given a nice similar set to the algebraic numbers, except now we're looking at functions. And for those functions, you can do any of the arithmetic operations. You can add, subtract, multiply, or divide algebraic functions to get new algebraic functions. And additionally, you can take roots anywhere you like. Could be square root or cube root, any root you want, you'll still get an algebraic function back. So far, we have this nice analogy between the first 3 sets of numbers and the first 3 types of function. And just like with numbers, there's this other category we throw in at the end. We say, oh, everything that we haven't described yet we'll call transcendental. So for transcendental functions, this means any function that isn't algebraic. And this includes things like exponential functions. We have 2 to the x as a function. So the variable here now is in the exponent. That's transcendental. We can't write it with roots or fractions or powers of x, because the x is in the exponent. And then if we get into trigonometry, there are functions there that are also transcendental. So I give an example here of the sine function. So sine of x would also be transcendental. The thing to remember, though, is just in the same way that you can organize functions in your mind with these 4 categories, you can do the same thing on real numbers. And this will help you organize all of the ideas as they come up in different examples and problems. Let's take a moment to look at some of these transcendental functions in a little more detail. You may have seen exponential or logarithmic functions before. You may not have seen them before. So let's just look at them as a type of transcendental functions. So they're not algebraic, they're not rational and they're not polynomial functions. So we'll call a function exponential if it has the variable x in the exponent. And so I've written out a few here that are good examples of exponential functions. So we might have 3 times the power 2 to the x. That's exponential. We may have a fraction to a power of x. So 1/3 to the x power, that's exponential. And then we may have simply a number to the power of x. And I've written e to the x here. And if you haven't seen that number e before, it's a number that comes up a lot in the sciences and in the natural world. So it's approximately 2.718, and that number gets its own name. So in that case, it is a number to a power of x, so it counts as an exponential function. Exponential functions, I've already said, they can show up in nature in various ways. This could include things like population growth or radioactivity, and both of those examples represent different kinds of exponential growth. So you could have exponential growth where the quantity is getting larger over time, or you could have an exponential decay where it's decreasing over time. So either of those can be modeled with an exponential function. The other kind of function that we'll consider here are logarithmic functions. And if that's a word you haven't seen before, just remember that it's the inverse of an exponential. So you're trying to do the exponential backwards. The way these look are we have various abbreviations, but the word log gets used for a logarithmic function. So you might have something like log x. You might have a log base 2 of x, or you might have ln x. If we see log x and there's no base specified, we assume the base is 10. In the second one, the log is specified as being a base of 2. And then if we see the ln, what we're really saying here is that the base is this number e. It's hard to write e precisely, so we don't bother. We just say ln for logarithm natural or natural logarithm. Now, getting back to what a logarithmic function is, we're thinking of it as being the inverse of an exponential. And I've done a very small example underneath, but what we're thinking here is that we have an exponential equation that we're trying to find the answer to, and we don't have a name for the answer, so we give it a name. We call it a logarithm. So when I write log base 2 of 3, I'm saying that's the solution to an exponential equation. In this case, it's the equation 2 to the y power equals 3. And that happens to be approximately 1.585. So if you go to a calculator and you take 2 to that power, 1.585, you'll get approximately 3. So thinking of a logarithm as just being the reverse of an exponential will help out a lot here when you're analyzing them. Just like with exponential functions, logarithmic functions show up a lot in nature. They're also used to describe certain things in the sciences that scale differently than we would expect. So the pH scale for acidity and alkalinity, that's an example of a scale that operates logarithmically. And then also the Richter scale or the decibel scale, if we're looking at earthquakes or sound, both of those are logarithmic scales. So lots of things are measured in this logarithmic way, which is why we have a name for it, and we're thinking of them as an inverse to exponentials. Let's finish by evaluating some of these functions for specific values of x. And what I mean by evaluate is for any function, let's look at the one on top for the moment. We have this polynomial function, and we want to evaluate at x equal to -2. So what that means is everywhere I see an x in that equation, I replace it with -2, and then I'll simplify. The result of that should be a number. And the other thing to remember about functions is we usually think of the function as giving you the y-coordinate. So if the x-coordinate is -2, then the answer that I get by evaluating will give me the y-coordinate. And you can see on the board there's 5 functions. They're following our different types of function that I had just talked about. So the first one is a polynomial. The second one is a rational function. The third one is an algebraic function. And then we have two transcendental functions at the bottom. One of them is exponential, and then the very last one is logarithmic. So we'll look at how to evaluate for the given x value across all 5 of those. But you will see this same procedure happening in each case. To get us started, let me give you a trick for thinking about evaluations. The form of the function might not be simple or nice, so to keep things organized in your mind, I recommend going to the function and then everywhere you see the x variable, put parentheses around it. So in this first case, I have 2x plus 1 being squared. Let's put a small set of parentheses around the x. And then I also have a minus x over here on the right. I'll put parentheses around that. And it seems unnecessary in the function itself, but when we get to evaluating it, you'll see how it keeps things from getting too confusing. So in this case, with number 1, I need to substitute in the value -2. I'll write this over to the right of the function. I'm interested in taking f of -2. There's our notation for it. Since I replaced x with -2, I'm doing that same thing across the whole expression. So I get 2 times -2 plus 1. I want to square that. And then I have minus x, but x is -2, so I'm doing minus -2. And at this point, we've evaluated. We haven't simplified. We don't know what that y-coordinate is, really. So let's simplify here. On the inside of the parentheses, I have a -4 coming out with a plus 1. So that ends up just being 3, -3 being squared. So in that case, I'll get 9. And then if I subtract a -2, that's the same as adding 2. So I could write that out as 9 plus 2. And now it's easy to see that I get 11 for that answer. So for this function, if x is -2, y is 11. Going on to the next one, I've chosen x to be 3 in this case. But let's do the same trick. Put parentheses around x everywhere we see it. It's showing up in 3 different places. Once we've done that, we can substitute. So we're finding f of 3. We substitute into the fraction. So there's 3 squared on top, and then minus 2 times 3. On the bottom, we have a 3 squared plus 1. So I'll write the 3 in parentheses, squared plus 1. And that's really the hard part. We do still need to simplify. And if we look on top, we have 9 minus 6. So that'll give us 3 on top. On the bottom, it's 9 plus 1, so 10. And we get 3/10. In fact, that's it. We're done. There's our fraction. So for this one, if x is 3, we've shown that on the graph, y will be 3/10. OK, let's continue on to number 3, putting parentheses around the x everywhere I see it. I can substitute in. We're looking at f of 8 this time. So to evaluate this function at 8, we have a square root on top with 1 plus 8 inside of it. And then on the bottom, we have 1 plus a cube root. And here it's the cube root of 8. I'll put the parentheses in, like I've been doing. And to simplify, we notice that on top, it's the square root of 9. That's 3. And then on the bottom, we need to do a cube root of 8, which happens to be 2. So I'll write both of those out. So square root of 9, 1 plus the cube root of 8. And we get 3 on top, 1 plus 2 on the bottom, which is also 3. So that's 1. OK, you get the idea. We have this trick where we can put parentheses around the x. And it's a way to organize the arithmetic so that when we get to simplifying it, we're not missing some order of operations issue. We can ensure that we really do get the right y coordinate for each one. Now, the two that might be new to you are the exponential and the logarithmic function. The exponential function will be pretty fast. And notice here the base of the exponent is 2. It is exponential because I have a power of x in the exponent. If we substitute in our -1, well, there's only one place to do it. That x shows up once in the exponent. So then evaluating is just a matter of putting that -1 in there. And we can see here how the parentheses will help us. So if I have -2, I'm subtracting 2, but then I'm multiplying that 2 by a -1, that's the same as adding. So I need to be careful about how I rewrite this. So I have 3 times 2 to the 1 plus 2 power. And from there, I get 3 times 2 cubed. There's always exponents involved in exponential functions. So we look at this, we say, okay, 2 cubed is 8 times 3 is 24. All right, so let's tackle the logarithmic one, and I'll do it a bit differently than the other ones, but it really does start the same way. So I can look at this and say to myself, well, 2 log 3 with a 9 in there is what I'm looking for. But I don't exactly know what that quantity is. I defined a logarithm as the inverse to an exponential, but it's an answer to a question. So what I'll do here is convert it from a logarithmic equation into an exponential equation. And using what I've said before, if we think of this value as being a y-coordinate, I can imagine y equals 2 times log base 3 of y. Now, to actually work out what that quantity is requires a bit of algebra. So let's go through those steps. We need to take this equation and make it an exponential equation. The first thing you should do is isolate the logarithm. That logarithm should be on its own on one side of the equation. So if I do that over here on the right, I'll take y divided by 2. I've divided that 2 over. That's equal to the logarithm of 9. So log base 3 of 9. And that's all I mean by isolating. That logarithm is on the right side of the equation, on its own. Everything else is on the left. And once I've done that, I can think of it as an exponent question, remembering that logarithms are the reverse or the inverse of exponentials. What we're really interested in here is an exponent where we have a base of 3. That's the same as our logarithm base. And we'll take the power of y over 2. So if I convert that over, I'm looking at 3 to the y over 2 power. I'm interested in when that is equal to 9. Now, at this point, it might not seem like we accomplished a whole lot. We did write it without logarithms, but what do we do next? Well, if we think of 9 as being a power of 3, then this turns into a matching game. So if we're looking at 3 squared on the right, that's 9. And on the left, we're looking at 3 to the y over 2 power. Then for this equation to work, I just need to have the exponents being the same. So if we pull off just the exponents, we have a y over 2 and a 2. We need those to be equal. And maybe now you can see what's happening next. I can solve that for y really easily. So y equals 4. But think back to what y was. Y was this function with 9 inserted in place of x. So what we've really shown is that f of 9 is y, and that's 4. So to evaluate logarithmic functions, you can put them back into an exponential form and reason through at that level to determine what the function should evaluate to. In all the cases, though, our very first step was to replace x with whatever value is given. And while the logarithms had a bit of extra work to solve it and figure out what that y value is, in all the other cases, it came down to simplifying. So let's recap everything we've seen in this video. We saw that there were 4 different types of real numbers. Those were integers, rational numbers, algebraic numbers, and transcendental numbers. We saw by analogy that there are 4 different kinds of functions. Those were polynomials, rational functions, algebraic functions, and transcendental functions. We then looked at how to evaluate those functions, which really just means to substitute a specific value of x into the equation and simplify. For logarithmic functions that involved a couple of extra steps, we needed to remember first that the logarithm is an inverse to the exponential. So once we had that idea, then to evaluate a logarithmic function, we can use a y equals equation with the value of x substituted into it. We can isolate the logarithm. And once we've isolated the logarithm, we can convert that into an exponential equation in order to solve it. As you think ahead to other topics, the key thing to remember from this video is that the process of evaluating a function gives you a y-coordinate. So if you're in a position where you're being asked to graph a function, all of these evaluation techniques give us an x and a y coordinate that we can then use to plot a key point or a point of interest in the two-dimensional plane that we're using to graph. Thanks for watching.